In this video, you're going to learn the quotient rule for differentiation. So remember that in mathematics, quotient refers to division or a fraction. So this rule tells us how to differentiate things in the form of one function being divided by another function. It's usually easy to recognize when to use the quotient rule because you've got to have this division present. And that's not true in the product rule, which I've linked to in this video in case you want to check that one out. The two rules normally go together. In the product rule, sometimes we disguise a product, but you can't really disguise a division. So it's going to be quite obvious when to use the quotient rule. So we're going to get to these example problems in a moment. Before we get there, let's just check out the rule itself. So the quotient rule says that if you're differentiating with respect to x, this division of functions, so f over g in this case, then that's going to be equal to f prime g minus g prime f, and then all of that divided by g squared. The important thing is not the letters f or g, because you'll see the quotient rule written in a bunch of different ways with different letters. The important thing is it's got to be the upper function's derivative first, multiplied to the lower function, which is not differentiated, just the lower function, minus the derivative of the lower function multiplied to the upper function, and then all of that divided by the lower function squared. So use whatever method you need to employ to remember that rule, because the quotient rule and the product rule are generally not given to you on a formula sheet. They might be, but generally not. Usually you've got to commit them to memory. Another way to remember it, which is maybe a little more compact, or another form, I guess, is if you let u and v be differentiable functions of x, so that's just some functions that have got x's in them, then the derivative of this quotient is equal to u prime v minus v prime u divided by v squared. So it might be easier to commit that version to memory than it is to commit this one to memory. The order is important though, because we've got a minus here as opposed to a plus. If it was a plus, it wouldn't matter on the order, but minus here means that you've got to get this one in the correct place and this one in the correct place. You cannot interchange them. So a good way to remember it, I think, is that it's the derivative of the upper function, the one at the top that goes first, and then you can kind of follow the pattern from there. So that's the theory. Start by committing that formula to memory. More importantly though, once you've done that, start applying it to different scenarios. So we're going to work these four problems now. You can see that these functions are all quite different. So we've got a mix of kind of polynomial functions. We've got a log function in here, a trig function. Doesn't matter what the individual functions are like, it just matters that we've got an overall fraction or an overall quotient, so we can use the quotient rule. So let's start by looking at this fairly entry-level type question. So we first of all got to check, is it in the correct format? Can we actually use the quotient rule? We can. We've definitely got a division of functions here. And you can imagine this being, you don't need to write this, but you can imagine this being your sort of f function divided by your g function. So I'll just write that in for this first example, just for illustration. So just so you can sort of align this question with the sort of formula over here. So we've got 4x is our f function and 2x cubed is our g function. So we're good to go. We just need to go ahead and plug this into the formula. So we're going straight to the derivative here. There's no work to be done before we differentiate because it's in a differentiable form for using the quotient rule. It's not in a differentiable form for using the power rule, and we're going to use the power rule as part of the quotient rule, so you need to be familiar with the first rule of differentiation, the power rule, before you can use the product or the quotient rules. So we could turn this into something that looks like the product rule, the power rule, and we could then use the power rule, but we're going to use the quotient rule on this example. So we're taking the derivative of f, so f prime of x, the derivative of 4x, which is 4, and we're multiplying that to g of x, which is the lower function, 2x cubed. So I'm just going to use a bracket to imply multiplication there, and then we're subtracting from that the lower function g prime, so the derivative of 2x cubed, which using the power rule is going to be 6x squared, and we're multiplying that to the upper function f, not changing that function, just leaving it as 4x like that. Okay, so it's a little messy, this rule. There's quite a few terms to deal with, and then it's going to be all of that over the lower function g, 2x cubed, squared, and it's all squared. So that's why we really need to use a bracket here. So it's going to be 2x cubed, all of that in a bracket to capture the squared. So at that point you're sort of done in the sense that you've used the rule correctly, hopefully, but it's quite messy. There's a little simplifying to do. Usually there is simplifying to do in this rule, and we just carry on and tidy up. So quickly multiplying out these brackets, so that would become 8x cubed. Here we're going to have 24x to the power of 3. On the denominator of our fraction, we need to square all of this, which means multiplying it to itself. So 2 times 2 is 4, x cubed times x cubed is x to the power of 6 using indices rules. So this would end up being 4x to the power of 6 like that. And this one we go a little further. We've got an x cubed term here, we've got an x cubed term here, so we could subtract those. So it's 8 minus 24x cubed, so you just got to carefully count that up. So I think that's negative 16x cubed, and then all of that being divided by 4x to the power of 6. That would actually go a little further again, because you can divide top and bottom by 4, and you can use one of the indices rules to simplify that down a little further. So I might just leave that one at that point and let you guys see if you can finish that off yourself. So that's just a basic implementation of the quotient rule. It's never really going to get much easier than that. And that's a very typical form, like these sort of polynomial type functions. Let's move on and have a look at the next one. So we've got this h of x function. Again, always check, is it in the correct format to use the rule that you want to use? That's what a lot of differentiation is about, checking the form, making sure it fits in with the correct rule, and then applying the rule. So yeah, definitely a function divided by a function, so we're good to go. So I'm not going to write in the f and the g this time, I'm just going to go straight to differentiating. So we can go straight to our h prime of x. So again, just maybe consult in the formula until you get used to it. So it's the derivative of the upper function first, which is just going to be 3 multiplied to the lower function. And once you've done enough of these, you'll start to go through them quite quickly. And then minus the derivative of the lower function, which is 2x, using the power rule, times the upper function, which is 3x minus 2. And then again, all of that over the lower function, which will quite often be multiple terms. So you need to put them all in a bracket because we're squaring them like that. And then again, at that point, you've performed the differentiation, but it's likely you're going to have some simplification to do. It's not always the case. I think in this one here, there's not going to be much simplification to do because we've got quite a simple lower function, but usually, especially with these polynomial type functions, there'll be 2 or 3 lines at least of simplification, but it's just kind of basic algebra. So multiplying out the brackets real quick, so 3x squared plus 3 minus 6x squared plus, for the double negative there, 4x. And then all of that divided by x squared plus 1 all squared. And then again, just scanning over to tidy this up. So we're going to have a 3, we're going to have a 4x, and we're going to have a negative 3x squared. Because of the negative 3x squared, I'm going to write this in reverse order. Normally we would put the highest power first, but I'm going to write it as 3 plus 4x minus 3x squared, just because that came out to be a negative. We don't like negatives on the left-hand side. And then all of that divided by the denominator, x squared plus 1 all squared. And that's all we can really do with that one. Sometimes you'll find that there's more can happen here and it might simplify down further, but that's not an untypical form for the final answer in the quotient rule. Sometimes it will neaten up a little like this, sometimes it will still be a little messy. It just depends on the original function, and you'll see all sorts, and you should try all sorts because you'll see various formats of the original function in these question types. Okay, right, let's move on, have a go at this one. So slightly different in the sense that we've got a trigonometric function, but it doesn't matter, like I said earlier, what the individual functions are. Just differentiate using whatever rule you've got to use. Again, ask yourself the question, can we use the quotient rule here? Is it in the correct format? Definitely is. We've got a function divided by a function, so we're good to go. So we can go straight to our dy dx. So hopefully getting into the swing of things now. So derivative of the upper function, derivative of sine x is cosine x, and we're multiplying that to the lower function, which is just x. Subtracting from that the derivative of the lower function, which is the derivative of x, which is just 1. So we don't really need to put in the 1. I'm just going to put in the 1 sort of for just illustration, I guess, times the upper function, which is sine x, and then all of that over the lower function squared, just x squared. And that's pretty much all you can really do with that one, because there's nothing that can happen to sort of combine terms. There's no like terms. All you could do is tidy up a little, maybe pull the x in front. We tend to put an x in front of a trigonometric function, so x cos x. That 1 obviously doesn't need to be there. That was just there for illustration, minus sine x, and then all of that divided by x squared. So a slightly different form, that one, but just using the rule in exactly the same way. There was no deviation from the rule just because it was a trigonometric function. We're just using the rule in the same way. Okay, so let's move on and have a look at our final example. So again, just asking yourself the question, can I use the quotient rule here? If for some reason you cannot use the quotient rule, then it's back to the drawing board and you've got to come up with something else. So definitely got a function divided by a function, so we're good to go. So we've got a logarithmic function here, natural log of x, on the upper part of our fraction divided by this x plus 1 polynomial or linear type function. So we can go straight into our derivative again. It's usually the case in the the quotient rule that it is ready to differentiate, because you will seldom manipulate a function into the form to then use the quotient rule. It will normally be set up already to use the quotient rule. Unlike, for example, the power rule, where quite often it's in a non-differentiable form and we do some algebra, some indices work or exponents work to get it into the correct form. These guys are normally good to go, because part of what they'll be testing you is that you recognize that the form is appropriate to use the quotient rule. So, derivative of the upper function, ln x, hopefully you know that one, it's 1 over x. So I'm not going to go into details of why that's 1 over x, but it is just 1 over x. And then multiplying that to the other function, x plus 1, subtracting from that the derivative of the lower function, x plus 1, which is just 1, times the upper function. Again, normally we wouldn't write in ones. It's not cool to write in ones, but I'm just putting it in there for illustration, just so we've got 1, 2, 3, 4 terms, which is what we're expecting from the rule. We're just learning the rule at this point, divided by the lower part of our fraction, x plus 1, all squared. And this one's a little, I guess, like this one. There's not a huge number of things we can really do now to combine terms or to tidy it up in any way. We could multiply this into the bracket. So 1 over x times x is x over x, which is just 1. So we get a 1 there. 1 over x times 1 is 1 over x. 1 times ln x is just ln x. And then the denominator of our fraction, nothing really can change there, so we're just going to leave it like that. So this one's come out to be in a pretty weird form, but think of it like this. If we didn't have the quotient rule, then we wouldn't be able to differentiate it at all. So if, for example, you needed to differentiate and then substitute in some number for x, which is quite often what we do in differentiation, then at this point you couldn't do that if you didn't know the quotient rule. Even though this has come out to be quite an ugly thing, if you were subbing in a number for x, after that substitution, it might simplify dramatically. And by using the quotient rule, you've been able to come up with some final answer. Okay, I might just go back and finish this one off. So I've got a little bit of space in here. So 16 divided by 4 is 4. We've got a minus in front, so it'll be minus 4. X cubed divided by x to the power of 6. Using exponent rules would be x to the negative 3. We would normally put that back down on the bottom of the fraction to have a positive power. So minus 4 over x cubed. Okay, so that's a few different styles of examples of using the quotient rule. So I would recommend that if you're kind of new to the quotient rule, you might want to also check out the product rule. The two tend to go together and they're useful to know together. So check out the link in this video to my video on the product rule. Otherwise, I hope that this has been a useful explanation of the quotient rule. And if you've got any questions or comments, then please just leave them in the box below.